All right, so we started. Let's not waste some time and let's start. So, hello everyone. I hope you're doing good. Today's event is Mars Launch by NASA. It's an event where our dear speaker is going to explain what was this very big trendy event made by NASA a month ago. Today's speaker is Dr. Martin. Professionally, Dr. Martin is a global project leader within the late stage development, respiratory, and immunology team at a major biopharmaceutical company based in Cambridge, United Kingdom. He has worked in all stages of drug discovery and development, from basic non-clinical and clinical science through uh, sorry through to both early phase 1 and phase 2 and late stage phase 3 and life cycle management, clinical development, managing both projects and established respiratory brands. Dr. Martin has published widely with over 200 publications and is a named inventor on 8 patents. He acts as a reviewer for project proposals for multiple European research agencies and has editorial roles on numerous scientific journals. In 2012, he was elected as a Fellow of the Royal Society of Biology for outstanding contribution to science. Outside of working in drug discovery and development, he is passionate about all aspects of astronomy and was elected a Fellow of the Royal Society of Astronomy in 2015 for his services to outreach activities. He has given over 100 presentations throughout Europe, Asia, and North and South America, contributed to several white papers for the UK Royal Astronomical Society, and is an active science, technology, engineering, and medicine. Through STEAM, he works through local schools and helps to inspire the next generation of young scientists at both school level and through UK-based astronomy societies, clubs, and groups. Guys, all useful links will be available in the description of this event once uploaded on YouTube. So please, if you have any requests, just raise your hand and write it in the chat box. Dr. Martin, the floor is yours.
Thank you very much. So let me just pull this up and make sure. Can you see my screen okay? Can you see the presentation?
Not yet.
Yeah, not yet.
Down at the right. It is down.
Yeah. So can you see it now? Ah, okay, here we go. It's coming.
Yes.
Okay.
It's working.
Oh, we can see it.
Right. Does that look good?
Yeah, it's
yes,
perfect.
of course.
Okay. So thank you very much, and thank you, Hadi, for your kind invitation and introduction. So I want to talk to you about the Mars lander Perseverance, but also start to introduce to us a little bit of thinking around what we may want to do after the exploration phase of Mars. And I think, as we all know, many space agencies and private enterprises are seeing Mars colonization by humans as a goal for the 2030s, and possibly even earlier than that, as organizations such as SpaceX, for example, have very ambitious plans. So I've worked in basic science, as you can heard from my introduction, and I'm also a member of Sherwood Observatory, which is in a county called Nottinghamshire in the UK. So what I'm going to do is take us through just a little bit of history of the number of spacecraft that there are now currently orbiting Mars, the journey for Perseverance, of course, the Jezero crater and why it was selected, and what will Perseverance do, and then start thinking a little bit about beyond exploration and the future for colonization for human beings. Martian agriculture, which is quite an emerging area at present, thinking of design considerations for perhaps what could become a new race of human beings. So Homo martis, rather than Homo sapiens, is perhaps where we may see human beings in 50 or 100 years' time. Then think a little bit about the Mars 1 mission, which started to work through habitat design for astronauts, and then finish with summary and conclusions. And throughout this presentation, I've credited NASA and JPL, the Jet Propulsion Laboratory, for all of their images, which are really outstanding and come in every day from Perseverance. So to start off with, what is happening at present? And of course, all the focus is on Perseverance, but there are two other spacecraft. One is the Hope spacecraft that's currently in an elliptical orbit around Mars from the United Arab Emirates. And that's already started to send back photographs of Mars. And its aim is again to understand the atmosphere of the planet. The second spacecraft is another rover from China, Tianwen-1. And this currently is also in orbit around the planet. And it's aiming to make its landing towards the end of May, early June. So in addition to Perseverance, we now have these two other spacecraft currently orbiting Mars, collecting a great deal of data that will be relayed back to Earth. Now, of course, this is a wonderful picture. I can never get tired of looking at rockets. This was the Atlas V rocket that launched Perseverance in July last year. What a wonderful image I think that is. And this is a very simple trajectory animation of the launch period. And of course, the launch period has been specifically selected because right now, this is where Mars is closest to the Earth. And there are various launch windows, of course, that all of the space agencies work to. So clearly, Mars isn't in a circular orbit around the Earth, as are many other planets around the Sun. So we have to time our orbits and time our launch windows to meet those orbits. So what an engineering triumph this is when you think about it. So this is some of the details here. It's part of, Perseverance is part of NASA's Mars exploration program. Of course, everybody thinks about Perseverance, but there is something else that's special too. And Perseverance carries a very small robotic helicopter. It's about the size of a small dog, and it's called Ingenuity. And the reason for that will become clear in a moment. So it was launched from Earth at 11:50 UTC on July the 20th. Touchdown, as we know, on February the 18th, traveling a little over 470 million kilometers. And the intention is that it will be on the planet for a duration of a year, which in Earth days is 668 sols or 687 Earth days. And that's the planned duration. The reality is, as we've seen from other missions such as Curiosity and Sojourner, is that the battery life will likely be longer than 1 year. So I'm sure we will see data from Perseverance collected over a 1 year period. So why have we sent it in the first place? And I think the reason can be summarized quite succinctly, as it's there to investigate what we believe to be an astrobiologically relevant ancient environment. And the part of the planet that it's gone to, the Jezero crater, has had a lot of surface geology in history. If there is anywhere that is likely to have signatures, biosignatures of life, either currently living life, which is very unlikely, or life that has been now long dead, extant life forms, this is one of the places that we're likely to find it. And the intent will be from Perseverance, it will drill into the surface it will take samples and it will cache them at various points along its route to be retrieved by a potential future Mars return mission. So there will be some analyses done on the planet itself, but it will be some time before we have authentic Martian, regolith Martian rock to work with back on Earth. And as I mentioned at the start, the test of a concept of a miniature helicopter is simply to see, would it work in a rarefied atmosphere? So we must remember that the Martian atmosphere is about 1% that of what it is on Earth. And of course, we all know how helicopters work. They generate lift with the circular motion of the blades. Would a helicopter work in an environment where the atmosphere is 1/100th the density that it is on Earth? And of course, that starts to then make us think about, is there the possibility of automated drones at some time in the future on Mars? So I'll give you some details now about the site of landing. And the site of landing here is in the circle in the left-hand side of this figure. So this is the crater. There is very, very high levels of information that tell us that water flowed into this crater. And I'll show you some of the actual details here rather than just an artistic impression. But the reason for landing in this place in the circle is that this is where signs of life might be found, simply because the water level in this crater would have led to the deposition of carbonates and other minerals that should be formed from organisms if they developed in the same way on Mars as they have done on Earth. And we can also see signs of where the highest level of water would be in the lake, in the crater, that again allows us to target perhaps where the rover should go to collect samples. So this is now some of the fine detail. And up in the top right-hand side here, you can see this is a classic river delta, exactly as you would find on Earth. So the structural homologs between water erosion on the Earth and water erosion on Mars are really quite remarkable. So a little bit more detail now about the engineering and what's on the Mars Perseverance rover. So if we start up at the top here, we have some zoomable panoramic cameras called the Mastcam Z, and it's these that are responsible for taking many of the pictures that we now are getting back on Earth. We also have a supercam, which is a laser micro imager, which is able to take pictures in absolutely exquisite detail. And I will show you some photographs in a moment. I find it hard to believe that we can have pictures of this quality from 500 million kilometers away. It really is quite astounding. There is also an automated weather station called MEDA, subsurface radar called RIMFAX, MOXIE, which produces oxygen from Martian carbon dioxide. So when I mentioned that the atmosphere on Mars is about 1/100th or 1% of what it is on Earth, that 1% is composed primarily of carbon dioxide. And last but not least, there are two items here on the right-hand side. Sherlock, which I'll tell you a little bit more about in a moment, which is an ultraviolet spectrometer, and there to hunt for potential biosignatures, complex molecules, and then Pixel, an X-ray spectrometer, which is also there to look for complex molecules. And then last but not least, this is an image here of the Ingenuity micro helicopter. Again, it's about the size of a small dog, which I think is around about 5 to 10 kilograms. So it's very small, but of course it's designed to test the concept of can it generate lift in an atmosphere that's very thin. So some of the details of the instrumentation, and if we look at the panel on the left-hand side, and this is taken from a wonderful paper published by Witzer in Nature last year. The idea, I guess we're all familiar with this, it's simply to use an ultraviolet laser on the surface, look for scattering and fluorescence, generate a spectral map, and then compare that with standard organic materials and minerals. And it's simply to ask what organics and minerals are there on the surface of the planet. Are we looking at just simple molecules, low molecular weight aromatics, or are we able to find more complex molecules, or are we even able to find peptides, amino acids, proteins? Are we able to find nucleic acids? Very unlikely, I think we recognize, but this will help us understand what complexity of organic materials there are. Now, the drill bit, I wanted to mention this because I think this is really key to the success of the mission. There's a just over a 2-meter long robotic arm that drills a sample of the rock, and then it brings the sample back to the underside of the rover, and it keeps it in these little vessels or caches, and then the intention is that some of these will be kept in the rover and some of them will be deposited on the surface of the planet as the rover makes its journey to be then collected in future. So this is a very nice cartoon representing the descent of the lander onto Mars. And if you've seen this, it's been called the 7 Minutes of Terror. And it's been called the 7 Minutes of Terror because, of course, when the spacecraft first enters the Martian atmosphere, it is going extremely fast, well over 3,000 kilometers per hour. And of course, at that speed, there is no way it would survive the impact. And if you're not familiar with this, I still pinch myself, as we say in the UK, as I can hardly believe the complexity and the beauty of the technology that's been used. So as the first steps of the 7 minutes occur and the lander starts to generate heat, it's slowed down by a parachute. The heat shield separates, so this separates completely after it's done its job. Of course, that reduces the weight, which reduces the speed. The back shell starts to separate, which again means that the lander has started to slow down. And then it has a powered descent. So the powered descent here is from jet engines on the underside of the lander. And then just to add to the complexity of the engineering, it's not this module that actually lands, it's this module that then deploys a sky crane, and the sky crane lowers the lander. Now, when the first attempts to do this with Curiosity were put into place some years ago, astronauts realized, of course, and mission scientists realized, if this was to land vertically, if this was to land vertically, then of course this part of the lander would land right on top of the rover. So it actually comes in at an angle and tilts slightly and then drops the rover, and because it's at an angle, this is able to fly away and then crash on the planet. So I ask you as engineers, can you imagine doing that on Earth, let alone on a planet that's 500 million or nearly 500 million kilometers away? I think it's absolutely fantastic technical achievement. And I captured this image from the NASA website. I think that is absolutely an astounding image, because it's somebody here literally holding their breath, perhaps praying at the same time, that as the lander starts to come down, that of course nothing will go wrong. And if you had the pleasure of watching the landing take place on NASA's live website, it's very brave to broadcast that to the entire world live, because of course there was no guarantee of 100% success. And I think that image just to be captures the excitement that there was at the time. So this is the actual photograph of the, you can see up at the top here, this is the parachute assembly, and this is now when we're starting to see the lander get deployed. And this is an actual image here of where the event was happening. And it gets better than that, because this is also the actual image of the rover being lowered on the sky crane. So this is not an artistic impression, this is the actual image. And you can see some of the detail here. It's not very clear of the surface of the planet as it's started to come down. And of course, this is one of the many scenes that was captured after the success. And again, you can just see here the joy that there is in mission control after the successful landing of Perseverance. And of course, again, everybody here having a quite rightly good celebration after the event. So these were the very first pictures that were brought back from Perseverance, and this was from the MADCAM. And of course, right at the start, it's taking some time for the instrumentation to settle and for the cameras to be cleared from the dust and for the dust to settle. But already, and I think this was within about 20 minutes of the lander having successfully, of the rover having successfully landed, we can start to see some really astonishing detail. So again, just look in this top left-hand panel here, some really, really good detail around the surface of the planet. What I wanted to mention here is just the precision that the lander had to go through. So this is now a heat map, if you like, of where it's safe to land in blue and where it's not safe to land or less safe to land in red. So this is the crater, and this is the outside rim of the crater. This is the precision that was able to put the lander into this particular safe area. So again, this is courtesy of NASA and JPL. Extraordinary engineering to be able to get it there, but also to be able to get it into a position of real safety. And this was one of the very first images. Now it's started to be a little bit clearer because the dust has settled, and this is in the panoramic camera, and you can see here just in the foreground, this would be exactly as you might find in arid regions on Earth, where you can see surface rock, you can see some very fine structures of detail. And this I find astounding. This is another image, and this is an image of a wind-blown rock. And again, this is courtesy also of NASA and the Jet Propulsion Laboratory. This could be anywhere on Earth. It just shows here that the physical wearing of this particular rock, more than likely carved by the wind, possibly water, but certainly all of the features here are exactly as you might find in the desert in your country and in arid regions in the Earth. In the United States, in Africa and elsewhere. So this again now starts to show a little bit more detail as to where the Perseverance landed. So this is the green dot, this is the delta here that I talked about a little bit earlier, and you can start to see now some of the structure. A little bit more here to actually show that it happened. So this is the Perseverance site, landing site. This was the descent stage. This is the parachute and the back shell that's been quite accurately located now on the surface. And right the way over here, this is the heat shield. So all of these component parts of the lander have been identified and they've all been shown, as by design, to be a long way away from the Perseverance rover itself, so that they don't in any way inhibit its movement or block it. And again, I can't get tired of looking at images like this. This is a very simple image looking at one of the treads on the rover's wheels, and again, just some of the very fine detail of the surface of the planet. So I mentioned a little bit earlier on that the rover has a predetermined voyage. And this is its predetermined voyage. So it will now start to take a look at various aspects of the crater and the crater rim itself and work on this predetermined voyage. And I'll show you a little bit now, again, around the image of the crater. So our lander is now in the crater itself, and it's now looking towards the outside. So in this large panoramic view, you can see the surface rim of the crater, and the intent will be that the rover will take samples along the bottom of the crater, but right the way up to the surface as far as it can get, because this is perhaps where life could be found. If you imagine all of this crater was full with water hundreds of millions of years ago, it's quite possible that there would be life forms buried within the rocks up here. And this is a larger image of that particular area that you can see in the middle here, with astonishing detail considering the distance. This cartoon, I think, gives you a good example of what the overall mission is aiming to do with its landing site here. It's going to deposit sample tubes right the way along. It's going to go up to various points on the rim of the crater here, as I mentioned, to take samples to see if they have any extant life or biosignatures, return them back to this place here where they'll be deposited on the surface, and then come up to this other area of the crater, take samples again and drop them off back here to be collected in future. So it's a well thought out and planned mission. It will be taking samples right the way throughout the crater and at the rim of the crater. And if there is ever a chance that we may be able to find signatures of life, hopefully this will be it. So last but not least, just in this part, just to tell you a little bit, of course, that we have, if you like, a giant server in space. So the Mars rover doesn't send data directly back to Earth. It uses a number of spacecraft that make up what's called the Mars Relay Network. And sending data from Perseverance directly back to Earth would simply take too long. So it sends data, and telemetry data in particularly, up to the Mars Relay Network. That data is processed, various signals are sent back directly to the rover itself, and data that is there for analysis back on Earth goes back to various radio antennae that make up what is called NASA's Deep Space Network that are at various points around the Earth. So this, in a way, if you like, is almost a very, very expensive server, if you like, or hub that we use for all of our computers, but the spacecraft around Mars also have their own hub. So that is around Perseverance. What I wanted to do now is spend about 20 minutes just going through with you now what we might think of as the future and building a brave new world on Mars. And I've been lucky enough to work with a number of colleagues over the years, and we've had a few publications now where we've started to think about, well, what could the future be for building a Martian future? And what types of considerations do we need to go through to start thinking about setting up a foundation to build the next, perhaps the next settlement of human beings, but off the Earth and on Mars? And what conditions do we need to think about that might help us get that foundation in place? So we started thinking about, is there a possibility that automated space colonization would need to happen before human space colonization? So if you imagine that we're now looking at sending people, 6, 8, maybe 10 people to Mars at the end of the 2020s, early 2030s, what do we want to do to give them the best chance of survival? And of course, we need to understand what risks are involved, what we can do to prevent those risks happening, and what we can do to provide countermeasures. There are a number of things that we would need to do, and that is to really establish some criteria for deployment of fully automated space vehicles. And these would be the types of things that could be used to 3D print structures in space, perhaps 3D print even the first habitats, certainly mine some of the materials that are on the surface of the planet, and generally make life easier for human beings that are going to arrive on the planet. And when we come to think about sending people to Mars, well, there are a whole number of psychological and physiological issues to think about. But one of the biggest things, of course, is thinking about setting up a new society, because with people that are possibly 500 million kilometers away, the chances of getting people back again may not be very great. So we're looking at establishing a separate society. And to me, it means that we have to consider both automated colonization of space and human colonization of space together. We have to see this as a way of helping people ultimately to help themselves. And this is a wonderful image from the Martian project, which has been developed by AI Space Factory. There has been a prototype 5-meter 3D printed habitat already constructed. So the possibilities of being able to do this ahead of arrival of the first colonizers is becoming slightly less science fiction and slightly more science fact. There is a huge amount that needs to be done to make this a reality. But if we're really going to have people live on Mars in the future, it's not too early to start thinking about what technology has to be put in place. So we need to think about sustaining people. And one of the interesting facts is that astronauts on the International Space Station, they consume about 1.8 kilograms of food and packaging per day while they're on the ISS. So if you multiply that by, let's say, a 2-year mission, and you have perhaps 6 astronauts, you can get to about 6,000 kilograms of food. And it costs about $4,000 to launch 1 kilogram of material into space. So you can imagine that it would not be possible to be able to launch enough food and water to feed astronauts for a 2-year mission. And one of the very interesting things that astronauts have started to work on with lunar regolith, yet to happen with authentic Martian regolith, is could regolith on Mars sustain plant growth? And I take this very interesting advertisement here. There is a group that's aiming to sell Martian soil, or a mimic of Martian soil. And of course, this is really for children rather than for adults. But the concept is quite interesting, because the types of analyses that have been done on lunar regolith may help us understand whether growing plants in Martian soil may become a reality. So I wanted to mention to you a little bit about work that I've been doing with a number of other investigators on exploring lunar agriculture as a potential model. And in the Apollo missions in the 1970s, there was very little known about lunar soil, as you would expect. And the first exposure of plants to lunar material was in about 1971, between 70 and 72. And it was all the way until the 2000s that we started to understand, could you actually grow plants in lunar regolith, in lunar soil? The bottom line is it's not really possible to grow plants in lunar soil unless there are supplements added, because of course there is no organic component. So you might think in that case, will Martian soil fare any better? So there are some potential stimulants for Martian soil that have been identified. And they started back in the 1990s, right the way up now to just last year. And the intent here is to look at the composition, take the data from the spacecraft that have been orbiting Mars, also now take the data, take the data from the rovers on Mars, and look at the composition, and then see, can we find replicants of that soil back on Earth? And of course, one of the things to note that Martian regolith has a high concentration of what we call perchlorates. Perchlorates are toxic to human beings. They're present at around 0.5% by weight of the regolith. They're also toxic to plants, so there would have to be a way to leach out perchlorates from Martian regolith to be able to grow plants on Mars. This is a study that was conducted some time ago, and it's looking at the percentage of germination, leaf formers, and plants forming flowers and still alive after 50 days. And it's comparing naturally occurring plants with nitrogen fixers and crops. Excuse me. And it's looking at soil samples in the Earth, Moon, and Mars. And of course, these are simulants rather than authentic soil samples. In most cases, you can see that the Moon samples fare pretty poorly when it comes to growing naturally occurring plants, nitrogen fixers, and crops. But Martian soil itself, for most of these points, is actually as good as, in some cases, slightly better at being able to sustain plants. So it makes us start to think, if we're ever going to get to a point where we have human beings on Mars, it might be a reality that we could grow crops in Martian regolith, not on the surface of the planet, of course, because the radiation is so high, but there may be some biosphere type environments where we could grow crops on Martian regolith. So I started working, as Hadi introduced me, I started working with a number of astronomy societies in the United Kingdom and asked them what were the 5 biggest challenges that they saw in establishing a human colony on Mars. And this is quite an interesting exercise. It was published in 2019. It took 387 people from 22 UK-based astronomy groups. And we started thinking through and then ranking what are the major challenges for colonization. And as you would suspect, many people said, well, food and water supply chain and storage is going to be the major challenge, mental health, effects of reduced gravity, economic justification. Why do we want to spend all this money on getting people to colonize Mars, for example? Provision of shelter, understanding effects of radiation, belief in a new start, and as you can see, working down this list. One of the things that really surprised us was that very few people thought that establishing a code of conduct was important. This ranked 10th in the analysis that we'd done. And that started us thinking, well, are there some lessons that we can learn from Mars analog studies that have been conducted on it? And the study that I want to refer to is called the Mars 1 mission. And the Mars 1 mission proposed this habitat design. So again, this is purely a concept, but it started to have people think about how would you physically live on Mars when you know that you won't be going back to Earth? How do you mentally cope with that? How do you physically cope with that? How would you design a place to live and work for life? And this is really the design that we put forward. And the design is actually here, it's for 4 people rather than 6 people, but there would be subsequent modules that could be bolted on. It's in an inflatable area, colonist space that is separate from storage area, from a greenhouse, from a sports and relaxation area. There would need to be the design for medical facilities and a communications station, manufacturing capabilities, most likely employing 3D printing, and possibly even 3D bioprinting. As I'm sure we're all aware, these days there's a very big impetus to want to replace meat as a protein product, and the possibility of using 3D bioprinting to print protein burgers rather than beef burgers or hamburgers It sounds a little perhaps silly, but it will become a reality, I think, on Earth. And those manufacturing capacities and capabilities could be deployed in any extreme environment, and Mars would be one of them. Then thinking through the surface design of ladder systems that would work through various subsystem modules starts to give us something like a proposed architecture that we might be able to work with. And some of the analogues that have been used in the past are based in, again, of course, extreme environments, the Concordia station based in the Arctic, the High Seas project based in Hawaii. And again, when you look at the geology here, you can see that there is a very great similarities with that that I've shown you on Mars. Likewise with the Flashline Mars Arctic Research Station, and then lastly the Mars Desert Research Station in Utah. So there are some analogues here to be able to learn from. And this is another facility called the Mars 500 facility that was set up in Moscow in Russia at the earlier part of the 21st century. A very similar design here, slightly larger, but the intent here is to have very clear and separate areas and a clear area here where there would be access to the surface. And some very interesting data published from this in the proceedings of the National Academy of Sciences in 2013. So the original study was this 520-day isolation experiment conducted between 2010 and 2011 in a 6-man crew. So these were all men, no women, 6 men, 3 Russians, a Frenchman, an Italian, Colombian, and a Chinese citizen. They included a simulation of Mars landing and 3 simulated Mars walks. And they all reported at the time optimal physical, psychological condition at the end of the mission. So after their 520 days in November and December 2011, they all reported that this was a perfectly happy, healthy environment to work in. But then 2 years later, and that's the purpose of this publication, it was reported that 4 out of the 6 crew members, so that's 2/3 of the 6 crew members, they'd started to develop sleep problems. They'd actually avoid exercise and would hide away from other people, a little bit as compared with animal behavior. And then they also experienced a disruption to their circadian rhythm during confinement. So the message from this is that for any confined environment to work in, which would be Mars if we ever get to the point of colonizing it, there is a lot psychologically that mission planners need to think through. This is not simple to take people, put them in a new environment and hope that everything will be okay. There needs to be some real thought as to what mentally may go wrong and then what we would be able to do about it. So I want to finish up just a little bit more futuristically now, having us think about human enhancement and the prospect of synthetic biology, because this is closer, I think, than most people would think. So to ask, first of all, is it realistic? Is it all hype? Is there actually some substance behind this? Is it advisable? I think the questions we always need to ask is it ethical? And then is it essential? And the reality is that with the technology called CRISPR, which is effectively DNA or gene editing, this is now at the point where studies are being conducted in human beings now in the clinic. And one of the best examples is correction of a particular gene for the treatment of LCA10. And I won't go into the details of LCA10, but this is a degenerative eye disease that leaves patients blind, and it's irreversible. So there is not a great deal to lose at least as far as patient eyesight is concerned, and that gene editing clinical trial is already happening. There is another study that's aiming to look at nanoparticle delivery of gene editing platforms to be able to deliver tissue-specific genome editing that was published at the end of last year. And again, that will progress into clinical trials. So why am I mentioning this? And the reason I'm mentioning this is that there are some potential ways that we might be able to enhance human beings to live on the surface of Mars. Radiation exposure, for example, is a key issue for anybody going to Mars or the Moon for that matter. There are some molecular targets that could be engineered to maybe make human beings less sensitive to radiation. There are also some molecular targets that could be engineered that may make human beings less sensitive to losing bone and muscle mass as a consequence of reduced gravity. So at present, gene editing to improve people is science fiction. Gene editing to be able to repair genetic level damages in people, for example, in the eye disease, possibly perhaps in cystic fibrosis and in Huntington's chorea, will become a reality, I'm sure, within the next 10 years. But this is just to sow in your minds the possibility that gene editing may be able to protect people living in harsh environments, such as on the surface of Mars, for example, from radiation exposure or reduced gravity. And of course, I should mention that the gravity on the surface of Mars is about 1/3 of the gravity that it is on Earth. So let's summarize now. So this gives you a chance for questions. Landing Perseverance and Ingenuity on the surface of Mars, I think, is an astonishing achievement, and I'm sure you would agree for science and engineering. And again, for the coders amongst you, I believe there are over 700,000 lines of code that went into the deployment of the Perseverance landing, and of course they all have to be checked, as we know. So the Mars 2020 mission paves the way, I think, for returning back samples to Earth for further analysis. We know that humans aren't well adapted to live and travel in space, and that automated preparation of a Martian base is going to be preferable before arrival of human beings. It might be possible to grow crops in Martian soil. And our little crowdsourcing exercise with UK has helped us, I think, understand a span for public opinion as to what the problems could be for future.
Hello, sir.
future colonization. So, to me, the space age is very much with us in 2021. When I was growing up in the 1970s, my parents used to say to me, "Martin, you're so lucky you're living in the space age." And here we are 45 years later, and we're still living in the space age. So I just want to thank you. This is my little giant step. And thank you for listening. And I'll do my best to answer any questions, Hadi.
Could you hear me, Dr. Martin?
Yes, I can hear you. So, do we have any questions? How will quantum computers help us? Well, I think in part the way that quantum computers will help us will be to process the data. I think for now, at least, integration of the data that is being collected is probably one of the biggest challenges that we have. And I think once we've got our collective understanding of the geography and geology of Mars, and perhaps an understanding of what weather there is on Mars, we'll be in a better position to know about the realities of colonization. Oops, do we have anybody else?
Yeah, I do have a question. Basically, it's a quote. I reckon that you know who Neil deGrasse Tyson is. He once quoted that if we have the ability to terraform Mars into Earth, we do have the ability to terraform Earth back into Earth. So, do you think that it's a must for us to return Earth back to the original, like back to the original value it had before even trying to colonize Mars? I mean, if we still didn't even fix Earth with all its global issues, its climate issues, and everything, will we be able to take these issues and just put them on Mars again and do the same thing like after like 100,000, a million years, a million of evolutionary years, yani later? So, what do you think, like, about about such question? Yani?
Yeah, I think it's a really good question, and my belief is we should be using this technology to not just go to Mars and other planets, but certainly to improve our position on Earth. And I believe it's your generation of people now, my children's generation of people, that as engineers, as scientists, will help us get out of the mess that we have on Earth. Because I think even within my lifespan, I've seen dramatic changes in the weather in the United Kingdom. We don't really have winters any longer. So I agree with you. I think all of the technology here, particularly the technology around recycling, will help us back on Earth. So I can tell you a story that it still resonates with me. I've only been to India once, and that was about 10 years ago. And what struck me in Mumbai is that everybody will recycle things. People make a living out of recycling things. In the United Kingdom, United States, most European countries, if something works, we just throw it away and buy another one. We don't recycle it. We don't think about repairing it. And I think that society has a great deal to learn about helping the earth to help itself, but at the same time, also developing the technology to be able to do it. And part of that will come from going to places like Mars. So recycling of water, for example, I think it's 98% of water is recycled on the International Space Station. Just think if we were to recycle 98% of water back on Earth, how that could help us for the future. So I agree, it's a good question. I agree.
Okay, Ali
Yeah,
Hamoud.
First, I would like to thank you for this amazing lecture. But I have a question. You said using the ultraviolet light, we can draw a spectrum to receive data of life. And it's not important to have a very advanced life forms, but it is life. So can we, from this data, analyze or receive the history of Mars in a more advanced way? And the data we receive, how can we improve for discoveries yet to come?
Yeah, that's a good question too. And I think in part, we can develop an understanding of what molecules we see as biosignatures. So as we know, we have 20 amino acids on Earth, but there have been other amino acids detected in meteorites, for example, that aren't our regular 20 amino acids. So part of what we can do, I think, is understand, is there a dependence of proteins to be made with the amino acids that we see on Earth? And if we were to find amino acids, complex or small complex molecules, what proteins could they produce if they were in the Martian environment? So I think there's a lot that we can learn, because we're looking at Mars from what we call an anthropic point of view. As human beings, we can only see what we know. but it's quite possible that carbon-based life can be formed with amino acids that aren't the amino acids that we have on Earth. And I think being able to identify what complex molecules we see on the surface of Mars, particularly if we find long dead microorganisms and microbes, I think would be astounding. And I think that tells us a great deal more then about what the potentials for life could be on other planets, on perhaps the moons of Jupiter, or maybe on Titan. I think there's a lot that we could learn from that. So we should be thinking about this as a way of understanding, are there other ways of making life forms with the biology and chemistry that we know on Earth, but using perhaps different components?
Thank you very much.
Nadine?
Okay, so you've never mentioned the part of carbon dioxide and oxygen percentages. What are they supposed to do so that they can take advantage of this carbon dioxide or something like that?
Yeah, so there's very little carbon dioxide, but the purpose for having that instrument on Perseverance is simply to say, could it produce molecular oxygen from the carbon dioxide that is there? And what NASA are trying to do is think, well, is there a way, perhaps in the future, of generating oxygen from the very thin atmosphere, in the same way that they're trying to think about how could we extract water from the frozen deposits at the poles of the planet. So all of these little experiments are being done to ask a question that may come in 5, 10, 15 years' time. Can we fly a helicopter, for example, in a very sparse atmosphere? Can we find ways to generate oxygen from the thin carbon dioxide? And can we find ways to extract water from the frozen deposits on the planet?
Thank you.
Welcome.
Mustafa?
Okay, I think my question is out of subject, but do you think in the future there's a possibility to reach or explore another galaxy?
Oh gosh. Well, this is really interesting, and Hadi, if you would ever like me back for another talk, I can tell you on something that I think it's we have to think about space travel perhaps not as physical human beings. And the reason I say that is the advances in machine-based learning are so quick that it's quite possible that we may be able to explore other galaxies and other planets virtually and not as physical human beings. So I think it would be possible one day, but I don't think it's possible for us to move spacecraft at the type of speeds that we would be able to do to visit other galaxies. But I'd happily share some thoughts with you for the future if you like.
Yeah, sure. I'll be waiting.
So I think we're nearly out of time, Hadi. I've seen a few people had to go. Where can we find the recorded meeting? Hadi has it. He has the presentation, so it's there for you. And please enjoy.
We will upload the recorded on YouTube. Malak has question.
Yes, please, if
Oh.
possible. First of all, Dr. Martin, thank you for this meeting. It was beyond amazing. I wanted to ask two questions, please. The first one is, do you think, like in the future, like, will it be possible, or at least a little less like than impossible, that we could navigate easily between Earth and Mars, like just like we navigate between, like, for example, countries here on Earth? like, you know, taking into consideration the very fast advancements of technology?
Yeah, I'm sure we will be able to do that. And I think we may even see this happen within this century. So I don't see any difficulty in being able to do that. The difficulty comes from getting back again. And I think part of the problem that NASA and all of the space agencies have is we're able now to land on the surface of the moon and land on the surface of Mars. With Mars, because there is more gravity than the moon. So the moon's gravity is about a sixth that of Earth. Martian gravity is about a third. There needs to be now more power required to get something off the surface of Mars. And that's something that the space agencies haven't worked out yet, because the only way of doing that at present is to take more propulsion with you to allow you to lift back off again the planet. So that's the next problem I think the space agencies have to tackle, but they will do it. I'm sure they will do it.
All right, one more question, please.
Sure.
Do you think, like, if human invasion happened on Mars, that we might like have to change our communication means, or will they still be the same? Like, for example, phones and stuff.
I think there is a physical part of human beings that would change if they were to live on Mars. So the intent would be ultimately that babies would be born on Mars, and they will develop differently because the gravity is less. Their bone structures won't be as strong as ours. Their muscle structures won't be as strong. They will also develop a different immune system. And I think we underestimate the powers of our immune system because we're exposed to microbes all the time on Earth. Most of us develop strong immune systems. Well, that won't exist on Mars because there aren't any microbes as far as we know. So human beings would develop very differently. And I think it then might be challenging for Martian-born human beings to come back to Earth.
Thank you, Dr. Martin.
You're welcome.
Okay, Hadi, the last question. Sorry, Hassan, we are running out of time.
Sure.
Should I ask my question, Shio?
Yes, Hadi, please.
Okay, so it's a bit of like a psychological question about like living in Mars. So basically, like, if you want to take volunteers, you have to take people that are willing to give up on Earth completely. Like, they know they're not returning back. So thinking about that, I mean, also Elon Musk said that, like, the chances of returning to Earth are very, very, very low, tremendously low, and you're gonna die there. If I want to put it into straight points, you're gonna die there.
Yes.
So how do you think, like, people can cope with such an idea, and how will you, like, provide a suitable environment, like, comparable to Earth in Mars, other than like Mars One or like Martia or like any of these like colonies and colonizations?
Yeah. Well, that's a good call. Hold on. So first of all, the question about would people volunteer to go to Mars? So you might be surprised how many hundreds of thousands of people volunteered, at least in the first instance, to go to Mars, knowing that they couldn't come back. I was quite surprised because I don't think that's something I would want to do. But there are a number of people, a lot of people, who are prepared to take that one-way ticket. I think the question of having a habitable environment, again, at present, this is science fiction, but if you've ever seen the film Total Recall, where Arnold Schwarzenegger is living on Mars, and in the background there are displays of mountains and cities and rivers, well, we can do that now. We can make ourselves think that we're living in an environment that's not true. NASA scientists have found a way to replicate the smell of cut grass, for example, to replicate the smell of pine trees. So it might be possible, it's artificial, but it might be possible to physiologically prepare people for working in these extreme environments. Now, would you want to do it for life? If you're in your 20s, do you want to spend 60 years of your life in those conditions? Those are very deep philosophical and ethical questions. Personally, if it was me, I wouldn't. But some people may be psychologically more happy to do that than others. And there is, of course, always the thinking of we are the pioneers of the future, explorers of the future, that may help individuals get through that. But it's a very good question, and I've spent some time with my colleague in Poland thinking through the ethics of how does a society police itself if people don't want to stay where they are any longer? How do you enforce law on a planet where there is no return back to Earth? So it's a very good question.
Thank you so much for the amazing answer.
You're welcome.
Thank you so much, Dr. Martin. Thank you all for attending this event. Feel free to contact Hadi Arwid, the chair, or me, Omar Banat, the vice chair, if you have any question. We will send a feedback link to know your feedback. Thank you so much all, and hope you enjoyed this event.
Oh, thank you, and please send me any feedback that that you would like to. If you liked it, please tell me. If you wanted me to do something different, please tell me. I'm very happy to help you, and thank you so much for being so engaged and asking such good questions.
Thank you, Dr. Martin.
Thank you.
We appreciate you.
Thank you, Doctor.
Bye.
Bye, Doctor.
Thank you for your time.
You're welcome.